If you are running an enterprise AI right now, the most expensive line item on your cloud bill isn't actually the AI thinking.
No, it's really not.
It's the AI trying to remember what it just read. We are talking about this hidden 10x storage multiplier that is quietly turning your vector database into a ticking financial time bomb.
Yeah, and it is the defining architectural flaw of the current AI boom.
Yeah.
I mean, everyone is so fixated on the cost of the large language model.
Right, the inference, the token generation.
Exactly. They're looking at that and completely ignoring the infrastructure sitting beneath it. But the reality of retrieval augmented generation, or RAG, is that, well, the memory systems are bleeding capital at just an astonishing rate.
Welcome to the deep dive. Today we are taking a really hard look at the hidden, spiraling infrastructure costs of RAG systems.
And to be clear, if you're listening to this, you might be an engineer tasked with scaling a cutting-edge prototype.
Or maybe you're a director of engineering or CIO staring down a massive, unpredictable AI budget.
Either way, this is the defining challenge of moving AI from like a really cool local demo to a sustainable production environment.
Yeah, absolutely. And we are pulling insights today from a phenomenal stack of sources. We have deep tech architectural analyses from Prasad Bond.
Who writes under the moniker the Quiet Architect.
Right, and Dr. Anthony Bolton. We're looking at FinOps blueprints from LeanOps, deep infrastructure breakdowns from the engineering team at Milvis.
And we also have insights on system pipelines from Ofer at Vectara.
And some incredibly provocative architectural philosophy from VSD data.
Which is going to blow your mind later on. But what is crucial to understand up front is that, our mission today isn't just to help you shave a few $100s off an AWS bill.
No, we're aiming to fundamentally rethink how enterprise AI handles memory, compute, and data hygiene.
Because the current default practices aren't just expensive. They are, quite frankly, wildly inefficient from a computational standpoint.
Okay, let's unpack this. We have to start at the absolute beginning of the pipeline.
Right, the ingestion phase.
Before we even get into vector databases or embedding dimensions or, RAM multipliers, we have to talk about what exactly is being fed into the system in the first place.
And our sources bring up this really interesting concept of junk vectorization.
Junk vectorization, that is a great term.
It perfectly encapsulates a massive operational and cultural flaw. Look at what happens when a company decides to build an internal AI assistant.
The mandate from leadership is almost always like, we want a cognitive engine that knows everything about our company.
Right. Every product, every policy, every historical decision.
The dream of the omniscient corporate oracle.
Exactly. So they just take the entire core to Google Drive, the massive SharePoint instances, the messy Confluence wikis, and they just pipe it all directly into the ingestion engine.
Without a single second thought. They blindly ingest uncurated legacy data into premium vector databases.
We are talking about 10-year-old out-of-office replies.
Oh, wow.
We're talking about 5 different duplicate draft versions of a vendor contract from like 2018. Expired promotional coupons, deprecated code repositories, endless threads of irrelevant Slack chatter.
And all of it goes directly into the embedding algorithms to be translated into vectors.
Yep, every single bit of it.
Let's talk about the financial reality of doing that, because Prasad Bone's analysis puts a terrifying number on it.
It's a huge number.
He notes that this practice of blind ingestion inflates AI cloud storage costs by roughly 70%.
70%.
Meaning, out of every $1,000 you spend housing your AI's memory, $700 is going towards storing absolute garbage.
It is the mathematical mapping of digital hoarding. I mean, enterprises have spent the last 2 decades treating traditional cloud storage as if it were infinitely cheap.
And for standard object storage, like Amazon S3, I mean, it largely is.
Right. You can throw terabytes of junk into an S3 bucket and just forget about it for pennies. The psychological hurdle that engineering teams fail to clear is recognizing that a vector database is not traditional storage.
How so? Like, what is the fundamental difference in the real estate there?
Well, vector storage is premium, high-performance memory. It requires specialized indices, it requires massive amounts of RAM, and, it requires continuous compute cycles to maintain.
So it's active, not passive.
Exactly. We are operating under the reality of asymmetric validation here. Every single kilobyte of vector memory has to mathematically justify its recurring operational expense.
Right.
If you put a 10-year-old out-of-office reply into a vector database, you are paying a premium tax on that document every single hour of every single day.
Just to keep it readily available for a high-speed mathematical search that will literally never happen.
Right. It's like paying premium downtown Manhattan rent to store a decade's worth of junk mail and expired coupons.
And then wondering why your monthly expenses are bankrupting you. But the cost is only half the problem, isn't it? Because keeping all this junk doesn't just waste money, it actively sabotages the AI.
Yeah, this is what Bond refers to as the information entropy law. Uncurated data inevitably degrades retrieval systems.
Okay, walk me through how that happens.
Well, when a user queries the AI, let's say an HR rep, asks about the company's remote work policy, the system converts that query into a vector and searches the database for the closest mathematical matches.
The cosine similarity search, it looks for the vectors pointing in the same semantic direction.
Precisely. But if your database is flooded with junk, you've polluted the data pool. The system might find the highly relevant, updated 2024 remote work policy.
Okay, good.
But it might also find a heavily discussed draft policy from 2014 and an angry email thread from 2020 debating work-from-home rules.
Oh, I see. And all of those mathematically match the semantic meaning of the query.
They do. So the system pulls all of them, feeds them to the LLM, and the LLM just gets completely confused.
It hallucinates a response that blends a 2014 rule with a 2024 rule.
Exactly. Your internal hallucinations spike. The signal-to-noise ratio is the fundamental dictator of an LLM's accuracy.
Right.
If you have too much noise, if you have too many vectors competing for relevance, your signal is lost. So cleaning the legacy data isn't just a FinOps exercise to save money.
It is a critical engineering requirement to make the AI actually usable.
Exactly.
So how do we actually stop this junk at the door? Because I imagine engineering teams aren't going to sit there and manually tag 5 million corporate documents to decide what gets vectorized and what doesn't.
No, nobody has time for that. It has to be automated, and it has to happen early.
The sources lay out a very specific strategy for this pre-RAG data sanitization, right?
Yeah, the first step they recommend is deploying a lightweight algorithmic proxy. They call it an edge script.
An edge script. And this sits before the embedding layer.
Yes. So before you even send the document to OpenAI or Cohere to be turned into a vector, you intercept it.
Right, because every document you send to the embedding API costs money. You want to drop the payload before the meter starts running.
Exactly. You intercept it at the perimeter.
But how does this edge script know what is a valuable corporate asset and what is just noise?
It relies on a telemetry audit. The script looks at the metadata of the files residing in your SharePoint or your Google Drive.
Okay.
Specifically, it looks for files with 0 access events in the trailing 36 months.
Ah, so if a document has not been opened, edited, or viewed by a single human being in 3 years, it is flagged as dead data.
Yep, flagged and dropped.
I have to push back on this because I can hear the objections from every data architect listening to this right now.
Oh, sure.
Isn't the entire promise of an enterprise AI that it acts as a perfect corporate memory? If we systematically drop files just because they haven't been touched in 3 years, aren't we lobotomizing the system's historical knowledge?
It is the most common objection.
Like, what if an engineer desperately needs to see the post-mortem report from a server crash in 2018 to solve a problem today?
Well, that objection fundamentally misunderstands the architecture of tiered knowledge. No one is saying you delete the 2018 server post-mortem from the company.
Okay.
You keep it, but you keep it in standard, ultra-cheap cold storage. It does not belong in your high-performance vector index.
Right, that premium Manhattan real estate.
Exactly. It comes down to a harsh trade-off. Is the extremely rare chance that someone needs a specific untouched 3-year-old file worth degrading the accuracy of every other daily query and inflating your cloud bill by 70%?
Yeah, when you frame it like that, the answer is obviously no.
For 99% of operational REA systems, the answer is no. So the edge script algorithmically drops those dead files, but it actually goes further than that.
How so?
It also analyzes document metadata and historical interaction telemetry to identify semantic redundancy.
Semantic redundancy. Give me an example of that.
Think about contract negotiations. You might have a folder with vendor agreement V1, V2, V3 final, and V4 actual final.
Oh yeah, we've all seen those folders.
Right. If you vectorize all 4 of those, you are paying for redundant storage and confusing the AI with conflicting terms.
Because V1 has different terms than V4 actual final.
Exactly. So the edge script identifies that these are sequential versions of the same semantic object, and it only permits the final signed version to pass through to the embedding API.
That is incredibly smart. So to solidify this pre-ARICAS sanitization, the sources suggest establishing a strict FinOps mandate.
Yeah, restrict vector ingestion to files accessed within the trailing 90 days.
If it's active, it gets vectorized. If it's dormant, it stays in traditional search.
And the compute capital you save by doing this is twofold. First, you avoid the embedding API fees.
Right.
And second, vastly more important, you avoid the recurring vector database hosting fees for that massive pile of junk data.
The ROI on this pre-rag sanitization is so massive that there are bootstrap startups entering the market offering this exact service on a shared savings model.
It's wild. They will install their edge scripts on your network for free, clean your data pipeline, and their only fee is taking a percentage of the vector database cost they save you.
That is fascinating. Do you think that kind of sanitization will eventually just become, a native feature of the big LLM platforms? Like, will Microsoft or OpenAI just build this filtering into their ingestion tools?
Well, it's possible, but you have to look at the incentives. The big API providers generate revenue based on compute volume.
The more tokens you send them to embed, the more money they make.
Exactly. The more vectors you store in their managed databases, the more money they make. They are not highly incentivized to help you aggressively shrink your data footprint.
So for the foreseeable future, pre-rag data hygiene is going to be a responsibility that falls squarely on the shoulders of your internal engineering and FinOps teams.
Absolutely. No one is going to clean your house for you if they get paid by the pound for your trash.
Okay, so let's assume we have fought that battle. We deployed the edge scripts, we ran the telemetry audits, and we successfully sanitized our data.
We only have pristine, highly relevant, active corporate knowledge left.
Right. Now, we have to convert that text into numbers. We have to create the vector embeddings.
And this brings us to Dr. Anthony Bolton's analysis, which reveals where the data size quietly and violently explodes.
Yes, the 10x amplification effect. This is the phenomenon that completely breaks traditional capacity planning.
It really does. When an IT director looks at a corpus of text, say, 10 gigabytes of clean, sanitized corporate documents, they assume they need roughly 10 gigabytes of database storage.
Which makes perfect intuitive sense. If I have a 10 gigabyte text file, I naturally assume I need a 10 gigabyte hard drive.
Right. But Dr. Bolton's math shows us why that intuition is totally wrong in the AI space. Let's walk through his breakdown.
Okay, let's do it. Let's start with just a tiny sliver of data.
1 kilobyte of raw text. That is roughly a few paragraphs.
Right. So what happens when that hits the embedding model?
When you send that text to an embedding model, the model translates the semantic meaning of those words into a high-dimensional vector. Let's assume a standard embedding size of 768 dimensions.
Okay, so 768 separate numbers representing the meaning of that paragraph.
Exactly. And in standard precision, each of those numbers is a 32-bit floating point decimal,
Okay.
which takes up 4 bytes of data. If you multiply 768 dimensions by 4 bytes, your vector is roughly 3 kilobytes in size.
Wait, so just the act of translating the text into math has tripled the size of the data?
Yes.
Your 1 kilobyte of text is now a 3 kilobyte vector.
And we are not even close to done. Because you can't just throw a million 3 kilobyte vectors into a database and expect to search them quickly.
Right, you need an index.
To achieve the millisecond latency that users expect, vector databases use specialized indices. The absolute industry standard right now is HNSW.
Which stands for Hierarchical Navigable Small World. I want to pause here because we hear HNSW thrown around constantly in AI infrastructure discussions.
All the time, yeah.
But rarely do we talk about what it physically is. Like, why does it take up so much space?
Think of HNSW as an incredibly complex, multi-layered map. You aren't just storing the data points. You are storing millions of navigational links between the data points.
Okay.
The small world part of the name refers to the 6 degrees of separation concept. The algorithm builds a graph where every vector is a node, and it creates edges or pathways connecting vectors that are semantically similar.
So if I have a vector about apples, it builds a pathway connecting it to the vector for oranges and maybe orchards?
Yes. And the hierarchical part means it builds multiple layers of these graphs, like zooming out on Google Maps.
Oh, I see.
The top layer might just have a few broad categories: fruit, vehicles, buildings.
Yeah.
As you drop down through the layers, the graph gets denser and denser until you reach the exact specific vectors at the bottom.
So it's basically a funnel for searching.
Exactly. This allows the search algorithm to start at the top, quickly navigate to the right general neighborhood, and drop down to find the closest matches.
Without having to calculate the distance to every single point in the database.
Right. It sounds incredibly efficient for searching.
For searching, it is a miracle of computer science. But structurally?
Structurally, storing all those millions of graph edges, all those layers and navigational links, requires a massive amount of overhead.
Right.
Dr. Bolton points out that building an HNSW index adds an additional 3x to 5x storage multiplier on top of your raw vectors.
Wow. Okay, so let's trace the math all the way through. You start with 1 kilobyte of raw text. You embed it, and it becomes a 3 kilobyte vector.
Yep.
Then you index it in HNSW, and that adds another 9 to 15 kilobytes of graph data. So your original 1 kilobyte of text has morphed into a 12 to 15 kilobyte high-performance data payload.
That is the 10x amplification effect. So when that IT director looks at their 10 gigabytes of clean text, they are not facing a 10 gigabyte storage problem.
They are facing a 100 gigabyte plus infrastructure challenge.
Exactly. And before we even deal with storing that amplified data, generating those vectors costs money.
Yeah, the LeanOps FinOps blueprint provides a stark breakdown of embedding model economics here.
A lot of developers, when they follow basic tutorials, they just default to using OpenAI's highest tier models.
Right, like they'll use text embedding 3 large,
Mhm.
which generates massive vectors with 3072 dimensions.
And the cost difference is staggering.
Mm.
The large model costs 13 cents per million tokens. But OpenAI also offers a small model, which generates 1,536 dimension vectors.
And what does that one cost?
That only costs 2 cents per million tokens.
Now, at first glance, the difference between 13 cents and 2 cents sounds trivial. I mean, if you have a corpus of 100 million tokens, the difference between the large model and the small model is only about $11 for a single indexing run.
Right.
Why is LeanOps making such a big deal out of an $11 difference?
Because of the hidden reality of iterative development. In a production environment, you do not embed your corpus once.
You're constantly tweaking.
Engineering teams are constantly tweaking parameters. They change their database schema, they adjust their metadata tagging, they realize they need to alter how they split the text.
And every time they make a change,
They have to re-index the entire corpus.
they wipe the database and run the whole thing through the API again.
Exactly. If a team runs a full re-index twice a week during a heavy development cycle over a massive enterprise dataset, you're suddenly bleeding hundreds or thousands of dollars a month just to recreate embeddings on a 3072 dimension model.
And the irony is, for most specific corporate domains, the smaller model would have performed virtually identically.
Exactly. Which brings us to one of the most powerful cost-saving strategies discussed in our sources: optimizing your embedding dimensions.
Right. You do not have to accept the massive default sizes.
The sources highlight techniques like Matryoshka representation learning and principal component analysis, or PCA, to drastically truncate embeddings.
We are talking about taking a 1536 dimension vector and chopping it down to 768 or even 512 dimensions.
This is where understanding the physics of dimension reduction is crucial. Every single dimension in a vector is a floating point number that the computer's processor has to handle.
Right.
When a user submits a query, the system performs a cosine similarity calculation against the database. It is mathematically calculating the angle between the query vector and the stored vectors.
And that math scales linearly.
Perfectly linearly. If you have a 768 dimension vector, the processor has to perform roughly twice as many operations to compute the similarity as it would for a 384 dimension vector.
Okay, I need to stop you there. Because if we are taking a 1536 dimension vector and just chopping off 2/3 of it to make a 512 dimension vector, aren't we throwing away massive amounts of semantic meaning?
It's a great question.
Like, how does the AI still understand the data if we delete hundreds of dimensions?
It is a brilliant question. And it is exactly why techniques like Matryoshka representation learning, or MRL, are so revolutionary. MRL is named after Matryoshka dolls.
The Russian nesting dolls, where a smaller doll sits inside a larger one.
Exactly. In a standard embedding model, the semantic information is spread somewhat evenly across all 1,536 dimensions. If you just chop off the end, you lose critical data.
Right, you'd lobotomize the vector.
But an MRL-trained model is fundamentally different. It is trained to front-load the most critical, core semantic concepts into the very first dimensions of the vector.
Oh, wow.
Yeah, the first 256 dimensions hold the broadest, most important meaning. The next 256 dimensions add slightly more granular nuance, and so on. The outermost dimensions hold only the most microscopic semantic details.
So it's a nesting ball of data. The core identity is protected in the center.
Precisely. Because of this architecture, you can truncate the vector, you can literally just chop off the last 1,000 dimensions, and the core semantic meaning remains completely intact in the remaining 512 dimensions.
That is incredible. And the LeanOps guide notes that truncating from 1,536 dimensions down to 512 dimensions drops your retrieval quality by a mere 2 to 3% on standard industry benchmarks.
But it cuts your storage requirements and your query compute cost by 66%.
66%. In high-volume environments, what we call high QPS, or queries per second workloads. That 66% reduction in math translates directly into needing significantly fewer compute nodes to handle your user traffic.
Exactly.
I look at this like image resolution. Do you really need an 8K uncompressed, massive raw image file just to train a self-driving car to check if a stoplight is red or green?
Absolutely not.
A highly compressed, low-resolution JPEG does the exact same job. The car still sees the red light perfectly, but the system processes the JPEG in a fraction of a millisecond for a fraction of the cost.
It's a perfect analogy. The 8K image technically contains more data. You can zoom in and see the texture of the glass on the stoplight, but for the specific task of determining the color, that extra data is entirely wasted.
It is operational bloat.
Yeah. And you have to wonder about the misaligned incentives in the AI industry right now. Do API providers default to massive 3072 dimension models because they are genuinely necessary? Or do they default to them to maximize their compute revenue?
Knowing that most developers will just accept the default settings without realizing the catastrophic downstream infrastructure costs.
Exactly.
Given everything we've seen, I lean heavily toward the latter. Now, beyond the dimensions themselves, the sources point out another major amplifier of data size, and that's chunking.
Oh, chunking. Yes.
This is how you cut up your raw text before you embed it. The LeanOps guide draws a hard line between naive, fixed-size chunking and semantic chunking.
Chunking strategy is often treated as an afterthought, but it dictates the entire shape of your database. Naive fixed-size chunking is the lazy approach.
Right. You tell a script, take this 50-page document and chop it into pieces exactly 512 tokens long.
Regardless of what the text actually says.
Exactly. It operates entirely blindly. This means it will inevitably slice right through the middle of a paragraph or right through the middle of a crucial sentence.
Let's walk through why that is so damaging. Let's say we have a dense paragraph explaining the liability clauses of a contract. The naive chunker hits its 512 token limit right in the middle of the explanation.
So you get two separate chunks. Chunk A contains the setup of the liability clause, but no conclusion.
Yep.
Chunk B starts mid-sentence with the actual legal penalty, but lacks the context of what the penalty applies to.
When you embed these chunks, their vectors are a mess. They point in weird semantic directions because they are incomplete thoughts.
Right.
When the LLM tried to retrieve the liability clause, it might only pull chunk B and then hallucinate the missing context from chunk A.
So to fix this, developers use semantic chunking.
Semantic chunking uses natural language processing to understand the structure of the document. It looks for paragraph breaks, header tags, and sentence boundaries.
It groups content by meaning.
It ensures that the entire paragraph about the liability clause stays together in one single coherent chunk.
And the cost impact of this is massive. According to the data, naive chunking, because it creates so many broken, overlapping fragments to try and preserve context, ends up creating 3 to 5 times more vectors than semantic chunking.
More vectors mean more storage, more RAM, and more compute.
But here is the trap that engineering teams fall into. If fixing chunking parameters is essentially a free software configuration, why don't teams just experiment with it constantly?
Right, why not try chunks of 500 tokens, then 1,000 tokens, then change the overlap from 50 to 100 tokens, and just see what works best in production?
Because of the hidden cost of reindexing that we talked about earlier.
Precisely. If you change your chunking strategy by even a single token of overlap, you invalidate your entire existing database.
Wow.
You cannot mix and match chunking strategies in the same index. You have to delete the database, pay the API provider to re-embed the entire massive corpus from scratch using the new chunking rules, and then burn massive compute cycles to rebuild the HNSW graph layers.
Doing that in a live production environment every week will bankrupt an AI project.
LeanOps strongly advises that you isolate a small, highly representative sample of your data, test your chunking strategy locally, lock it in, and never touch it again before you index at scale.
Okay, let's take stock of where we are. We have intercepted the junk data at the perimeter. We have chosen a smaller, optimized embedding dimension using Matryoshka.
We have chunked the text semantically so we aren't generating millions of useless fragments.
We have squashed the data down as much as physics allows. But now, these highly optimized vectors have to physically live somewhere.
And this brings us to the most brutal reality of RAG infrastructure. the crippling reliance on RAM.
This is the juncture where traditional database engineers get a very rude awakening. In a traditional relational database, like a standard SQL server, the data lives permanently on a hard drive, usually an SSD.
Right.
When a query comes in, the system uses the operating system's page cache to pull only the specific data it needs into memory, process it, and then flush it back out. Memory is used dynamically and sparingly.
But you're saying vector search is fundamentally different.
It is an entirely different beast. Vector search is nothing but massive, parallel floating point computation.
To deliver that ChatGPT-style experience where the answer begins streaming instantly, those complex HNSW graph indices, the millions of navigational links we discussed generally need to stay fully loaded in RAM at all times.
Why? Why can't the HNSW graph just sit on a fast NVMe solid-state drive?
Because of how the graph is traversed. Finding a vector in an HNSW index requires jumping rapidly and unpredictably from node to node across the different layers of the graph.
This is called random access traversal.
Right. Hard drives, even the fastest SSDs in the world, are designed for sequential reading blocks of data in a line.
Oh, I see.
When you force an SSD to perform millions of tiny, scattered random reads to traverse a graph, you hit an I/O bottleneck. The latency spikes from milliseconds to seconds.
So the only way to traverse the graph fast enough is to hold the entire architecture in random access memory.
Exactly.
And as we all know, RAM is incredibly expensive cloud real estate. The Milvus engineering team breaks this down, and the numbers are sobering.
Memory accounts for 85 to 90% of a vector database bill.
Let's look at the real-world math provided by Jack Lai from Milvus.
If you have a corpus of 10 million vectors operating at full 32-bit float precision using an HNSW index, you need approximately 64 gigabytes of RAM just to hold it in memory.
Okay.
On a cloud provider like AWS, an EC2 instance with 64 gigabytes of memory is going to cost you roughly $310 a month.
Now, $310 a month might not sound terrible for a mid-sized company, but what happens when that prototype scales? What happens when you go from 10 million vectors to 100 million vectors?
Suddenly you need 640 gigabytes of RAM.
You are paying thousands and thousands of dollars a month just to keep idle memory powered on, waiting for a query. It scales disastrously.
So how do we escape this RAM trap?
Well, the industry is aggressively evolving to push this data back down to disk without ruining latency. The primary strategy discussed in our sources is tiered storage.
Tiered storage.
This involves a sophisticated caching mechanism where memory usage drops to under 10%. The system identifies the hot data, both the vectors that are queried frequently, and keeps them in RAM. The warm data sits on local NVMe SSDs, and the cold, rarely accessed data is pushed out to cheap cloud object storage like S3.
Wait, if the cold data is on S3, doesn't that ruin the user experience? If someone queries a cold vector, won't it take the system 10 seconds to fetch it from the cloud?
Yes, there is a latency penalty for a cold start query, but you mitigate this with intelligent routing. If a query hits cold storage, the system can stream a filler response.
Like searching historical archives.
Exactly. While it fetches the data, it is a UX trick to mask the latency. The cost savings of not holding cold data in RAM far outweigh the occasional latency bump.
The sources also talk about mmap, or memory mapped files. How does that work?
mmap is a fascinating operating system level trick. It maps the data files residing on the local SSD directly into the process address space of the database.
Okay, so it essentially tricks the vector database into thinking the hard drive is actually RAM.
Yes. The OS only loads specific pages of data into physical memory on demand. As long as you're using exceptionally fast NVMe drives, the latency penalty is acceptable for many enterprise applications, and the RAM savings are massive.
But the biggest lever for escaping the RAM trap, the optimization that seems to yield the most dramatic results, is scalar quantization. Explain the mechanics of this, because it sounds like magic.
Scalar quantization is a brutal but highly effective form of compression. We established earlier that standard vectors are made up of 32-bit floating point numbers.
These are highly precise decimals.
Scalar quantization takes those complex 32-bit decimals and mathematically crushes them down into simple 8-bit integers.
Hold on. You are taking a high-precision number and stripping away 75% of its data. Doesn't that completely ruin the AI's ability to find the right answer?
You would think so.
If the numbers aren't precise, how does the cosine similarity search know what is actually a match?
It is the most counterintuitive part of vector math. You would think that stripping precision destroys accuracy, but it doesn't. Because cosine similarity isn't looking for the exact absolute coordinates of a point in space.
Right.
It is looking for the relative direction of the vector. If you have an arrow pointing northeast and you slightly degrade the precision of its coordinates, it is still pointing generally northeast.
Ah, so its relationship to the other vectors remains intact.
Exactly. The relative distances between the vectors are preserved well enough for the algorithm to find the correct neighborhood.
That's amazing.
The economics of scalar quantization are undeniable. It slashes your RAM requirements by a factor of 4. Taking that previous example, your 64 gigabytes of RAM needed for 10 million vectors instantly drops to just 15 gigabytes.
Wow.
Now, instead of needing a $310 a month instance, you can fit the entire workload on a $155 a month instance. You just cut your infrastructure bill in half by flipping a configuration flag.
But to realize those savings, you have to make a fundamental decision about where and how you are hosting this database.
The LeanOps guide provides a brutally honest breakdown of self-hosted infrastructure versus managed services. Let's walk through these trade-offs, because this is where a lot of teams get paralyzed.
It is a critical fork in the road. LeanOps starts by addressing the low end of the spectrum. If you are building a small internal tool and you have under 2 million vectors, their advice is simple. Do not buy a dedicated vector database.
Just use pgvector.
pgvector being the open source extension for PostgreSQL.
Right. Most companies are already running standard PostgreSQL databases for their normal application data. Adding the pgvector extension allows that existing database to store and search vectors.
It carries near zero incremental infrastructure cost. It is the most financially efficient way to start.
But what happens when you outgrow pgvector? When you cross that 2 million vector threshold and need dedicated architecture, LeanOps points to self-hosted options like Qdrant or Milvus.
Self-hosted options are incredibly cost-effective for mid-range, high-volume workloads, say 5 to 20 million queries a month. That is where that $155 a month quantized instance we just talked about really shines.
Right. You rent the raw compute from AWS or Google Cloud, install Qdrant yourself, and you pay hardware prices.
But there is a massive catch.
The catch is the human cost of operational overhead. You are no longer just an AI developer. You are now a database administrator.
You are managing complex Kubernetes clusters. You are responsible for configuring the storage volumes, setting up high availability replicas, managing disaster recovery backups, and monitoring memory pressure.
And if that self-hosted Qdrant cluster crashes at 2 a.m. on a Sunday, it is your engineering team whose pagers go off.
Exactly. You have to factor in the hidden exorbitant costs of site reliability engineering, or SRE salaries. A single senior SRE costs significantly more than a managed cloud database.
Which naturally leads teams to the managed services, the serverless platforms like Pinecone, Zillus Cloud, or Wie Geht.
Managed services are the easy button. They abstract away all the infrastructure. You just send them vectors via an API, and they handle the RAM, the scaling, and the backups.
LeanOps notes that these serverless options are fantastic for prototyping because you usually pay per read-write unit. If no one uses the app, you pay very little.
But the danger of serverless is what happens when you are successful. If your app goes viral, or if it is deployed enterprise-wide and receives tens of millions of queries, paying per read unit becomes exponentially more expensive than just renting a server.
Which is why LeanOps recommends transitioning to pod-based or dedicated pricing tiers once you scale. Pinecone, for example, offers pods where you pay a fixed hourly rate for a slice of dedicated infrastructure, regardless of how many queries you run against it.
The mathematical crossover point where fixed pods become cheaper than serverless read units is generally around 8 to 10 million queries a month.
There is another major factor pushing companies toward managed services, and our source offer from Vectara coins a brilliant term for it: vendor chaos.
Vendor chaos is the hidden tax of the DIY modern data stack. When you build your own R pipeline from scratch, you usually glue together a Frankenstein's monster of services.
You have an embedding model from Cohere. You have a self-hosted Milvus database on AWS. You have an LLM from Anthropic doing the generation. And maybe you have a separate re-ranking model from a fourth vendor.
So what happens when a user types a question into the chatbot and the chatbot confidently returns complete garbage? Or the latency randomly spikes to 15 seconds.
That is the nightmare. Who do you blame? Is Anthropic hallucinating? Did Milvus drop the index from RAM? Did Cohere's API time out? Diagnosing pipeline failures across 4 disparate vendors, checking 4 different sets of logs, is an operational disaster.
This vendor chaos heavily incentivizes companies to use unified, managed platforms.
Exactly. Traditional enterprises do not want to act as systems integrators. They want a single unified pipeline, what some call RAG, as a service, where the ingestion, the embedding, the storage, and the generation are all handled in one box.
They want a single throat to choke when things go wrong.
Before we leave the topic of databases, we absolutely have to discuss multi-tenant architectures because the LeanOps guide highlights this as the area where B2B companies are literally setting money on fire.
Let's paint the scenario. You build a brilliant RAG-powered SaaS product, say, a legal contract analyzer. You sign up 50 different law firms as clients.
The immediate instinct of any security-conscious engineer is to build 50 separate vector indexes, one isolated database for each client, to ensure data privacy.
And from a pure infrastructure cost perspective, that instinct is suicidal.
Why? If the total amount of vectors is the same, why does it matter if they are in one index or 50?
Because of base overhead. Every single index you spin up in a vector database carries a baseline resource requirement, regardless of how many vectors are actually in it.
The system has to reserve a baseline chunk of memory.
It has to spin up background maintenance threads for compaction. It has to establish replication rules. If you multiply that base overhead by 50 or 500 or 5,000 clients, your infrastructure costs explode, even if most of those clients barely have any data.
So what is the solution? How do you maintain strict data isolation without going bankrupt on base overhead?
You utilize a shared multi-tenant index with strict metadata filtering. All 50 law firms share the exact same underlying infrastructure resources, the exact same index.
But every single vector ingested into that database is hard-tagged with a metadata identifier, for example, tenant ID law firma.
And when a user from law firm A executes a query,
The backend system silently appends a strict, non-bypassable filter to the query. Before the algorithm even calculates a single cosine similarity, it filters out all vectors that do not match tenant ID law firma.
the math is only performed on their specific slice of the database.
According to LeanOps, executing this simple architectural shift from isolated indexes to a metadata-filtered shared index reduces per-tenant infrastructure costs by an astonishing 80 to 90%.
And it does not compromise data isolation or privacy at all.
It is arguably the highest impact architectural decision a B2B SaaS company can make when building a hard product.
Okay, let's take a mental breath. Look at what we have accomplished. We have sanitized the data with edge scripts. We have compressed the embeddings with Matryoshka learning.
We have chunked it intelligently. We have picked the right infrastructure, leveraged scalar quantization to slash our RAM usage, and consolidated our clients into a shared multi-tenant index. The database is a lean, mean, optimized machine.
But we are still not safe.
No, we are not, because the way the system actually searches through these pristine vectors can still burn an unbelievable amount of money. It is time to look at the exact moment a user hits enter, the query phase.
This is where the compute cycles really start spinning. Storing data is a static cost. Searching data is an active recurring compute cost.
And the biggest culprit driving this active compute cost is a little obscure algorithm parameter called fsearch. Let's really break this down, because tweaking this one number can change everything. What is fsearch?
Fsearch stands for F, which usually denotes the size of the dynamic list for the nearest neighbors during the search phase of the HNSW graph. To put it simply, it controls the size of the entry point candidate pool.
Okay, so when a query enters the HNSW graph, fsearch dictates how many neighboring vectors the algorithm is allowed to look at before it decides it has found the best matches and returns the final results.
So it's the thoroughness dial.
Exactly. It dictates how exhaustive the search is. And the defaults in almost every major vector library are set remarkably high, usually around 200.
Why 200?
Because the developers who built these libraries want them to look good on academic benchmarks. An fsearch of 200 ensures maximum accuracy. It guarantees roughly 99% recall, meaning the algorithm is 99% certain it has found the absolute mathematically closest vectors in the entire multi-million node graph.
But the compute cost to achieve that 99% certainty is astronomical. The LeanOps guide strongly recommends dropping that fsearch parameter down from 200 to 50.
Let's look at the math of that drop. Moving fsearch to 50 reduces your recall from 99% to roughly 95%.
You are theoretically losing a tiny bit of mathematical precision.
But because the algorithm is looking at a fraction of the candidate vectors, it cuts your per-query compute cycles by 60 to 70%.
I look at this like losing your car keys. And a search of 200 means you are searching your entire neighborhood. You are knocking on neighbors' doors. You are shining a flashlight down the storm drains. You are retracing your steps 3 blocks away.
You are burning massive amounts of energy just to be 99% sure you didn't drop them down the street.
Which is exhausting and incredibly inefficient.
Right. But an fsearch of 50 means you just check the obvious places. You check your coat pockets, you check the kitchen counter, and you check the floor of your car.
You are 95% likely to find your keys in those 3 spots, and it takes you 2 minutes instead of 3 hours.
It is a phenomenal analogy because it highlights the core issue. The perceived difference to the end user is zero. If the AI retrieves the 5 most relevant documents to answer a question, the user does not care if those documents were the 99th percentile mathematically perfect matches or the 95th percentile matches.
The generated answer will be functionally identical.
This highlights a fascinating problem of engineering culture. Why do engineers leave it at 200? Because engineers are naturally incentivized to chase perfection. They want the system to be flawless.
But they are completely ignoring the FinOps reality. Moving from 95% to 99% recall literally doubles the compute cost for an invisible benefit.
You are paying a massive premium to search the extreme edge cases of your vector space. By tuning F-search to your actual business requirements, you save a fortune.
And while we're on the topic of query efficiency, we have to talk about caching. Because what happens when a user asks the exact same question someone else asked an hour ago? Or worse, what if a user just hits refresh on their browser?
In a naive, unoptimized system, the entire heavy pipeline starts from scratch. The system takes the prompt, pays the OpenAI API to generate a brand new vector embedding, sends that vector to the database, burns compute cycles traversing the HNSW graph, retrieves the documents, and feeds them to the LLM.
Which is an absurd waste of resources for a question you already know the answer to.
The LeanOps guide suggests short-circuiting this process by building and embedding cache using a fast, lightweight memory store like Redis. But they don't suggest caching the final text response, which is what most people assume.
Right. You generally do not want to cache the final LLM text response. If you cache the text, our remote policy is 3 days in office, and HR updates the policy the next day, your cache is returning invalid, hallucinated data. Caching final text in dynamic environments creates massive invalidation headaches.
So what are we caching in Redis?
You cache the mapping between the query vector and the retrieval results. When a user asks a question, you generate the embedding. Before you search the expensive vector database, you check Redis. You compare the new query vector against the vectors of previous queries.
If you find a previous query vector that has a cosine similarity of greater than 0.97 compared to the new query,
they are functionally identical questions. What is the WFH policy versus what is the remote work policy?
Exactly. The math proves they are the same intent. So instead of traversing the database, Redis instantly returns the IDs of the documents that were retrieved last time.
You bypass the heavy vector search entirely. LeanOps data shows this simple semantic cache can save 30 to 70% on API calls and query compute in environments with overlapping user questions.
Okay, speaking of keeping things clean and efficient, we need to go over the LeanOps audit and prune checklist. Because even with all these optimizations, vector databases act like magnets for dead weight. They accumulate waste incredibly fast if left unattended.
They absolutely do. The biggest hidden culprit of waste is orphaned indexes. Think about the daily life of an AI engineer. They are constantly running experiments.
They want to test a new embedding model, so they spin up a new index in the database, they run their tests, they get their benchmark results, they close their laptop, and they completely forget to delete the test index.
And because vector indices require base memory overhead, that forgotten experiment sits in RAM, consuming expensive resources forever.
Forever. So, action item number 1 on the pruning checklist. Implement an index usage log. You must architect your database to record the exact timestamp of the last query executed against every single index.
Which gives you the visibility for action item number 2. Set a strict 30-day archival or deletion policy. If an index has not received a single query in 30 days, an automated script kills it or at least drops it out of RAM and into cold storage.
LeanOps notes that when companies run this audit for the first time, they routinely surface 10 to 20% of their total vector database spend as immediately recoverable waste.
Action item number 3 deals with how vector databases actually handle data deletion, which is counterintuitive. You have to manage the data lifecycle using compaction.
The Milvis engineering team has a great breakdown of why this is necessary. Vector databases are fundamentally designed to be append-only architectures. They are built to ingest data as fast as humanly possible.
So when I send a command to delete a vector, say a document is outdated, the database doesn't actually remove the data from the disk.
No, it does not. Because physically finding and erasing that data in the middle of a complex graph structure takes too much time. Instead, the database simply attaches a tombstone marker to the vector. It flags it as deleted.
The algorithm ignores it during a search, but the vector is still physically taking up space on your hard drive and in your memory structures.
So your storage bloats with ghosts.
Precisely. To physically remove the ghosts, you must run compaction. Compaction is a heavy background process that sweeps through the database, merges small data segments, restructures the graph, and physically permanently deletes the tombstone data.
If compaction is so great at cleaning up the trash, why not run it constantly? Why not have it running in the background every second of the day so the database is always perfectly pristine?
Because compaction is incredibly I/O intensive. It requires reading and rewriting massive amounts of data on the disk, and it consumes significant CPU cycles.
If you run a heavy compaction process during peak user traffic hours, the disk gets overwhelmed. Your I/O bottlenecks, your read latency spikes dramatically, and your live production queries will start timing out and crashing.
You have to schedule compaction carefully, treating it like heavy database maintenance, usually during off-peak night hours or weekends.
Got it. And the final action item on the checklist, implement a TTL, or time to live, on ephemeral data.
This is critical for temporal data. If you are embedding system logs or historical user session behavior to provide personalized context, that data loses value very quickly.
An error log from a month ago is useless today. You configure a TTL of 7 or 30 days. When the timer expires, the database automatically tombstones the vector, and the next compaction cycle sweeps it away.
The database becomes self-cleaning.
So, if you have followed us this far, we have built an incredibly lean, efficient, highly optimized RAG pipeline. The data is pre-sanitized, the dimensions are squashed via Matryoshka, the database leverages mmap and quantization, the upsearch is tuned for maximum ROI, and automated scripts are aggressively pruning the waste. We have saved a massive amount of money.
It is a textbook, perfectly executed FinOps infrastructure.
It is, but our final source, VS Data, drops a philosophical and architectural bombshell on all of this. They look at this perfectly optimized RAG pipeline and claim there's a fundamental lie at the center of enterprise RAG.
It is a profound critique. Because VAS Data isn't arguing that we optimize the pipeline poorly, they are arguing that the very nature of the pipeline itself is broken.
The lie is that the current infrastructure treats every single prompt, every single user query as a brand new isolated event. It forces the GPUs, the most expensive hardware on the planet, to rebuild the exact same context window over and over again from scratch.
We've spent an hour talking about the cost of the vector database. But we have to look at what happens when the vector database hands the retrieved documents over to the LLM.
We have to talk about the pre-fill phase and the KV cache because this is where the real inference compute is being burned.
Break down the mechanics of the pre-fill phase. What is the GPU actually doing when it receives the documents?
An LLM is inherently stateless. It has no memory of its own. When you ask it a question and provide 5 retrieved documents for context, the GPU has to ingest all that text. It converts the words into tokens.
Then it runs those tokens through massive transformer blocks to calculate the relationships between every single word.
It calculates attention matrices, how much attention the word contract should pay to the word liability. This massive, dense matrix multiplication results in a massive data structure called the key value, or KV cache.
So the KV cache is essentially the AI's working memory. It is the mathematical representation of the AI understanding the documents you just handed it.
Exactly. Building that understanding the pre-fill phase takes an immense amount of GPU compute power. VS Data points out that pre-fill compute is currently eating the economics of enterprise AI. It is vastly more expensive than the actual generation of the words in the final answer.
Let's use an analogy to make this concrete. Imagine you hire a brilliant lawyer and you hand them a dense 500-page legal brief. It takes them 3 hours of intense focus to read it, understand the cross-references, process the liability clauses, and hold it all in their working memory. You ask them one specific question about page 42, and they answer it perfectly.
That 3 hours of reading is the pre-fill phase. The understanding in their head is the KV cache.
But then, the moment they answer the question, the lawyer instantly gives themselves amnesia. They completely wipe their memory of the document. An hour later, a different partner walks into the room and asks a question about page 45.
The lawyer has to sit back down and read the entire 500-page brief all over again from scratch. That is exactly what your GPUs are doing right now.
Because the KV cache is currently trapped in temporary, ephemeral runtime memory on the GPU. The moment the chat session ends or the query is resolved, the hard-won, computationally expensive contextual understanding is destroyed. It is thrown in the trash to free up VRAM for the next user.
Which is absolute madness. VS Data's proposition is that we need to fundamentally change the architecture. We need to make the KV cache durable and persistent. We need to save the AI's memory.
If a support agent queries a massive product manual, the GPU burns the compute to build the KV cache. VS Data argues that instead of throwing it away, we should stream that KV cache data structure down to high-performance disk storage.
If a second support agent queries that same manual an hour later, the system recognizes the intent. It doesn't rebuild the context. It routes the request to the warm, persistent KV cache that already exists on the disk.
It skips the massive GPU prefill phase entirely.
You just eliminated the most expensive compute phase of the entire operation.
And if we connect this to the bigger picture, making KV cache persistent completely collapses the traditional boundaries between storage, retrieval, and inference.
Right now in traditional RAG, those are three separate disconnected silos. Data lives in object storage. We retrieve it with a vector database. We infer meaning with an LLM on a GPU.
But if the memory of the inference, the understanding itself, is saved as a storage asset.
Exactly. The system stops asking what raw text is relevant and starts asking what understanding already exists in the system. The infrastructure changes from a chain of disconnected tools into a continuous, unified cognitive architecture.
Let's extrapolate this, because this concept is the foundation for the future of agentic workflows. Everyone in the industry is talking about AI agents, autonomous bots that can execute multi-step tasks.
Imagine a team of AI agents constantly passing tasks back and forth. One agent reads code repositories, another checks compliance documents, another analyzes financial models.
If they are all dumping their KV cache after every action, the compute cost is impossible to scale. But if the KV cache is persistent and shared,
the persistent KV cache becomes the shared version of the entire company. When Agent A reads the compliance document, it writes its understanding to the shared storage. When Agent B needs to reference compliance, it instantly accesses Agent A's understanding.
the semantic work compounds over time. The system gets smarter and exponentially faster because it remembers what it has already processed, rather than throwing its memory in the trash every 5 minutes.
But hold on, I have to play devil's advocate here. A KV cache is a massive, highly uncompressed data structure. If we start saving the KV cache of every major document processed by the company forever, doesn't that just create a new massive storage problem to replace the old one?
We just spent an hour figuring out how to shrink our vector storage using Matryoshka and quantization. Now we are going to store terabytes of massive KV cache matrices on disk.
It is a brilliant point, and you have identified the exact bleeding edge of AI engineering right now. Yes, persistent KV cache requires massive, high bandwidth storage, but this is exactly why storage-first AI architectures are the next evolution.
You are making a calculated trade. You are turning inference memory, which was previously pure ephemeral compute waste, into a managed, highly valuable enterprise asset.
Storing data on disk, even complex KV cache data, will ultimately be cheaper than renting NVIDIA H100 GPUs to recalculate that data a million times a day. Storage is becoming the foundation of intelligence.
What an incredible journey this has been. Let's briefly recap how we systematically dismantle these hidden R costs. We started at the absolute perimeter, the ingestion layer, dropping dead corporate data with edge scripts and 36-month telemetry audits so we aren't paying a premium to vectorize 10-year-old out-of-office replies.
We squashed our embedding dimensions down from 1536 to 512 using Matryoshka learning, saving massive space while preserving core semantics. We fixed our chunking.
We made incredibly smart database bets, leveraging mmap and scalar quantization to crush our vectors into 8-bit integers and escape the exorbitant RAM trap. We consolidated our tenets.
We tweaked our search proximity thresholds, dropping S-search to save massive compute cycles on a query. We set up automated pruning to kill orphaned indices.
And finally, we looked to the horizon, where persistent KV caches might just save the AI from its own constant computationally expensive amnesia.
It is genuinely a masterclass in FinOps engineering. If a team implements even half of this checklist, they will rescue their AI budgets.
But this comprehensive pursuit of efficiency raises an important question, a final thought for you to mull over. We have spent this entire deep dive optimizing for leanness.
We rigorously sanitize data. We aggressively prune unused vectors. We set strict 30-day deletion policies and 90-day retention limits on ingestion to save money.
We made the machine perfectly efficient.
But in doing so, do we risk engineering an enterprise AI with corporate amnesia? If the AI only remembers the recent, the highly accessed, and the popular, How will it ever help us uncover long-term cyclical trends?
How will it learn from past forgotten failures that haven't been accessed in 3 years, but suddenly become relevant to a new crisis today?
Wow, we systematically pruned the serendipity right out of the system. We optimized away the messy historical accidents where true innovation usually hides.
Exactly. Is the relentless pursuit of perfectly lean infrastructure costing us the very deep historical insight we wanted from artificial intelligence in the first place?
That is a fascinating, almost haunting tension to end on. You, the listener, have to decide where that balance lies for your own systems and your own company's culture. Thank you so much for taking the time to join us on this deep dive. Take these checklists back to your engineering teams, challenge your defaults, audit your pipelines, tune your parameters, and whatever you do, stop letting those vectors silently bleed your budget dry. Until next time.